In this video, we consider the language L, which is the set of strings that are descriptions of Turing machines, M. So it's a set of strings M such that M is a Turing machine, and M accepts all odd numbers. We need to show that L is undecidable. Remember, our standard proof of decidability is to find a undecidable language that we can reduce to L, and then we can conclude that L must be undecidable by showing a proof by contradiction. What we're going to do. What we're going to do is to reduce ATM to L. So let's think about how we could reduce ATM to L. Given a decider for L, so let's start by suppose that D is the decider for L. Okay, so D is able to say if a Turing machine, given a Turing machine description, does the language of the machine contain all odd numbers? Does it miss any odd numbers, or does it have any even numbers? So our idea is going to be to construct a decider for ATM that itself is going to construct another machine that accepts all odd numbers if and only if M accepts W. So that's what we're going to do. Let's construct a decider, let's call it A, for the language ATM as follows. Okay, so what does A do? Well, remember, it's going to get input that looks like machine description and then a string. Okay, we're going to use the machine description and W, the string, to construct a new TM, let's call it M prime. And what does M prime do? Remember, M prime is going to accept all odd strings if and only if M accepts W. That's our plan. Okay, so it's going to take on input X, where X is a string that's going to represent a number, either an even number or an odd number. So on input X, if X is even, reject. Okay, so we accept no even numbers. Otherwise, so if we pass the first step, then X must be odd. We are going to simulate M on W. If M accepts W, then we're going to accept X. Okay, so notice here that M prime is automatically going to reject all even strings. So if we get to step 2, it's because X is odd. And then after we simulate M on W, we only accept this odd string X if M accepts W. Notice that it will accept every odd string X if M accepts W. So no matter what input X I give it, as long as it's an odd string and then M accepts W, we're going to accept that odd string. Notice that if M does not accept W, we accept nothing, right? M prime accepts nothing because it rejects all the even strings right off the bat. And then if M accepts W, we don't go ahead and accept X. Notice here we don't explicitly say that we reject because it's possible that M could run forever on W. So M prime itself is a recognizer, not a decider, but that's okay because we're never actually going to run M prime. We're going to feed its description to D, which is the decider for L. Okay, so here, okay, I'm out of the description for M prime, so back into my description for A. It has constructed M prime, and then in step 2, it's going to run D, my decider for L, on M prime. Okay. And if D accepts M prime, reject if D does not accept. Actually, I'm just going to say reject. Here I really mean the same thing, but we're going to be super clear. Reject if D rejects M prime. Okay. So first, let's make sure that A is a decider, so that's important. Given a machine description M along with a string W, we're going to go through and construct this machine M prime, and then we're going to run a decider D for L. Since D is a decider, on every input, it's either going to halt and accept or halt and reject. Okay, so the step 2, we're going to get an answer yes or no, basically, from D, and then we give the same answer, yes or no. Okay, so we are guaranteed to halt and accept or halt and reject. So basically, we're guaranteed to halt on every input MW. Okay, so we know this is a decider. Now let's make sure that this is a proper reduction from ATM to L. So let's see what happens. So if A accepts the string MW, why does it do that? It does that because D accepts the machine description M prime. Why does it do that? It does that when X is odd and M accepts W. Okay. Do I really want to say that? That's really not. Let me make this better. Otherwise I have to go into a case by case fashion, and I don't want to do that. Okay, so D accepts M prime when the language of M prime contains all odd numbers, and it does that when M accepts W. This is better. Okay. All right. So we have that A, our decider for ATM, is going to accept MW when M accepts W. Okay, so this is correct for our acceptance, and let's check our rejection. So A rejects MW when D rejects M prime. When does D reject M prime? When the language of M prime is empty. Okay, notice that the only things that M prime is ever going to accept are odd numbers. And the only time it accepts odd numbers is when it accepts all odd numbers, when M accepts W. Otherwise, it accepts nothing. Okay, so D is going to reject M prime when the language of M prime is the empty set, when it has nothing in it. And this happens when M does not accept W. Okay, so A accepts MW when M accepts W, and A rejects MW when M does not accept W. So this is, in fact, a decider for ATM. Okay, we know that ATM is undecidable. Therefore, we cannot construct a decider for ATM. And constructing the decider for ATM hinged on D, the existence of D, that there is some decider for L. So we know we have a contradiction. D can't exist, and therefore L is also undecidable.